Ready to roll.
Very good. Good morning, good afternoon, or good evening, wherever you are. As you know, this is the first workshop of a series of the workshops uh, on Fault Displacement Hazard Initiative. Uh, I give you a short presentation about overview of the project, and then we will go over the agenda, different speakers. So before really we start, I want to acknowledge the supporters of the project: California Energy Commission, Caltrans, California High-Speed Rail Authority, PG&E, SoCalGas, and LA Department of Water and Power. All of them contributed partial supports. Also, we have had serious technical partners, including SCEC, California Geological Survey, and JPL. We really appreciate all the supports and cooperation of partners and funding agencies. So the goal of Fault Displacement Hazard Initiative, FDHI, is to update fault displacement hazard analysis by expanding the database, empirical database of fault displacement, and then developing fault displacement predictive models. And we will go over each today, Wednesday, and Friday. Like our other large projects like NGA, this has been a community-based research project. Many people have been working on different pieces of the project. And since we wanted to do something impactful rather than just writing a paper, so we have had serious interactions between academic researchers as well as practicing professional. This is really what we have been doing the last 20 plus years in our large community-based research projects. So motivation is that any lifelines that crossing faults, including, for example, natural gas transmission pipelines, water transmission pipelines, water tunnels, transmission tunnels, high-speed rail, Caltrans, any distributed lifelines that they cross faults, they really have to consider fault displacement hazard as one of their major hazards. The outcome of the FDHI has been two pieces: database and models. Database, which Alex today also is going to elaborate on that. It's a relatively large database, includes 75 earthquakes, magnitude 4.9 to 8, over 40,000 measured displacements, and the database is fully available to the public. We already published it. You can use this click and download the database. This is a figure that Alex put together. Vertical axis is the magnitude of the data. Horizontal axis is the name of the earthquakes. The largest earthquakes magnitudes that we have, they have two magnitude 7.9 and one magnitude 8. But majority of the data, as you see in the right-hand side, the magnitude is between 6.5 to 7. Most of the data, almost half of the data is coming from strike slip faults. After that, reverse. After that, normal, which as you expect. It is an international database. We collected the data from all around the world, as you see from the map, and you see from the pie chart. Most of the data is coming from Western North America, followed by Japan, and then Australia and others. It is really international database, again, similar to our other large projects. The second major contribution of the project, FDHI, is four fault displacement hazard predictive models. I'm not going to read the names. You will see that, and all the modeler teams will have presentations, especially on Wednesday. They will give you an overview of their models and key features of their models. The status of the models is that the models are final. We went through multiple iterations. Modelers team corrected and updated their models. The models are final. Multiple reports have already been published. Multiple journal papers have already been submitted, and they are going through review process. In fact, a few of them already have been published online in Journal of Earthquake Spectra, ERI Earthquake Spectra. And also models have been coded in Excel and Python, and Alex on Friday is going to show you the coded version of the model that you don't have to code it yourself, because they are a little bit complicated models. Another outcome of this project, in the middle of the project, we decided that it's good to have a probabilistic fault displacement hazard map for the state of California. Similar to the ground motion hazard that you enter the location, it gives you PSHR results. That was the idea, to have it for fault displacement hazard. You enter the location, it gives you probabilistic fault displacement hazard. We don't want to oversell these things. It's good for preliminary assessment and screening. It will not replace the site-specific investigation like any other maps. And the map and the data will be available in early 2025. Steve Thompson is going to elaborate on this issue, on this task, on Friday. So as you know, we are going to have 3 days of workshop, 10 a.m. to 12 noon Pacific time, Monday, Wednesday, Friday. Today is the first day, and we give an overview of the project, and we give an overview of the database and the metrics and so on. Wednesday will be busy. All the developers, model developers, they give overview of their models. And then on Friday, you will hear the comparisons of the models as well as implementation of the models. So we are going to distribute PDF of slides as well as the link to video recording to the registered participants. So if you miss, for example, today, Wednesday or Friday, you will have an opportunity to quickly catch up. Last, please enter your comments and questions in the chat box. And then Alex is collecting all the questions and comments. And during the session of QA, we are going to go over as many questions as possible. Otherwise, we'll communicate with you offline. Appreciate that. Thank you for your participation. About 230 people registered for this workshop. And as you know, some people cannot make it, but is very, very interesting and popular subject, and we appreciate your participation. After me, Dr. Rui Chan is going to give you an overview of fault displacement hazard process analysis. So let me stop sharing this, and because I have two monitors. So I stopped and I invite Rui. Welcome, Rui.
Thank you, Yusuf. Do you see my screen?
Yes. Looks perfect.
Okay. I am Rui Chen with the California Geological Survey. I'll give an overview of Fault Displacement Hazard Analysis, or FDHI, with a focus on the probabilistic approach, or PFDHA. I'd like to thank Steve Thompson, Brian Chu, Rob Moss, and Alex Sarmiento for their contribution to this talk. here's my outline. I will go over some basics of FDHI first, talk about PFDHA framework, which is basically a process of integrating over multiple probability models. And then I will step through each component model and trying to point out what is or is not part of this workshop. So what does FDHA do? Well, it provides a quantitative estimate of the amplitude of fault displacement at the surface from future earthquakes. A central part of FDHA is fault displacement model, which is also the central subject of this workshop. There is a deterministic approach and a probabilistic approach. The deterministic approach, DFDHA, calculates displacement using fault displacement models, often at the desired exceedance probability. The probabilistic approach, or PFDHA, calculates displacement hazard curves using fault displacement models and other probability models. There are similarities and differences between the two approaches. They both incorporate variability in displacement. They both can incorporate uncertainty in earthquake sources, although DFDHA is for specific scenarios. PFDHA incorporates probabilities of surface rupture. DFDHA typically does not. PFDHA considers the rate of events. DFDHA does not. There have been many application examples of FDHA. The most well-known is the success story of a Trans-Alaska oil pipeline in which a deterministic approach was used. The pipeline subsequently survived the magnitude 7.9 Denali earthquake. There are applications for nuclear installations such as Yakmantin, Diablo Canyon, Krsko nuclear power plant in Slovenia. For lifelines, California high-speed rail, it's used by Caltrans, BART, LA Metro, PG&E, etc. And for other structures like UC Berkeley Stadium and other structures, Aliso Canyon gas storage field, and dams. For the rest of my talk, I will concentrate on the PFDHA. PFDHA was introduced by Bob Jans and others in 2003. They proposed an earthquake approach and a displacement approach. The earthquake approach is similar to PSHA for ground motion hazard, with ground motion models replaced by fault displacement models. It requires additional probability terms to account for the occurrence of surface rupture. Displacement approach treats surface ruptures as independent events without reference to causative earthquakes. It requires sufficient site-specific displacement measurements and their occurrence times to establish statistical models. Jans et al. Also distinguished the two types of displacement and rupture, principal and distributed. This map shows surface rupture and displacement measurement points from the 1992 Landers earthquake in the FDHI database. Purple indicates principal and cyan indicates distributed. Steve Thompson will explain the definitions, including what's principal and what's distributed later this morning. Most of my talk, as well as this workshop, is about the earthquake approach. Most of the new fault displacement models are also applicable to this approach. Here are some common variables used in PFDHA for a site and a fault. The thin dark line represents the fault mapped before an earthquake. The thick dark line is the surface rupture from an earthquake. Z is the dimension of site area considered for probability of surface rupture. Delta is the closest distance from the site to the rupture. Lowercase l is from the point on the rupture closest to the site to the end of the rupture. Capital L is the total surface rupture length, and S is from the end of the rupture to the end of the fault. Now, principal displacement is regressed as a function of the normalized location on the fault, which is this L to L term. Distributed displacement is usually regressed as a function of rupture distance, or delta here. Now I wanted to talk about a PFDHI framework, including hazard equations and the data needs. Now I mentioned PFDHI is a process of integrating over multiple probability models. This particular equation is modified from Peterson et al. 2011. The actual number of terms differ slightly in the literature, and they can also be different for principal and distributed displacement. In this particular form, which is for principal displacement, besides source characterization, there are 4 probability terms. The first one is probability of surface rupture given magnitude. Empirical models such as Wilson-Kuppersmith 1993 model have been developed using earthquake catalogs of events with and without surface rupture. This term is needed because not all earthquakes rupture the surface. Given an earthquake ruptures the surface, surface rupture does not occur everywhere. So the second term accounts for the probability of rupture crossing the site. And it is often characterized by analyzing high-resolution surface rupture maps such as this one. The third term is also probability of rupture crossing the site, and it is due to the uncertainty in the location of future surface rupture, or location uncertainty. In Peterson et al. 2011, this term was quantified by distances between surface rupture and the pre-event fault map, fault trace. The last term is a conditional probability of displacement exceedance, which is basically fault displacement model developed using fault displacement data. I will talk about each of these terms briefly in the next few slides. Source characterization can use the source characterization for PSHA, except often only sources closest to the site need to be considered. And also greater detail is needed for fault geometry. Now, source characterization is not a major part of this workshop, but it is an essential part of any application. And Steve Thompson will talk about example applications on Friday. Probability of surface rupture given magnitude. The first and the most widely used model is Wilson-Kuppersmith 1993 model. It was developed using a global database that contained all styles of faulting. According to this model, 45% of magnitude 6 earthquakes produce surface rupture. That percentage is 87 for magnitude 7. Later studies found styles of faulting and other factors affect this probability term. So they developed models that are specific to a faulting style. Some are regional, others are global. Now the predictions from these models can be very different. Recently, Lisa Memorella, Steve Thompson, and others explored a numerical approach that considers source parameters. Lisa will give a lightning talk on Wednesday, introducing her work. These colored curves are example results from Steve for source-specific fault. Now, they found all magnitude 7 earthquakes ruptured the surface. So this probability is 100%. For smaller magnitude, they found that the average fault width plays a very important role. This is from statistics of catalogs that are dominated by reverse fault. For example, if fault width is 13 kilometers, this probability is only 12%, but it is 95% if the fault width is 6.5 kilometers. And this is compared to the 45% prediction from the Wilson-Coppersmith model. So you can see there's a very large range. Probability of rupture crossing the site. One method to determine this probability is using cell counting approach, where the probability is equal to the ratio of cells with rupture and the total number of cells at a given rupture distance. Now, for principal rupture, which is at the 0 distance, Peterson et al. 2011 derived these ratios. However, they suggest for this probability term to be 1 for large strike slip faults in California. And many practitioners also assume this probability to be 1 if site-specific data show a primary fault crossing the site area. Probability of rupture crossing the site area due to location uncertainty. From a small number of earthquakes, Peterson et al. 2011 derived these statistics that depend on the accuracy of mapped fault trace and the complexity of fault geometry. There's ongoing work at Arizona State University, which will help us better understand this term. Alternatively, the way to treat this or fault location uncertainty is to treat it as epistemic. Conditional probability of displacement exceedance or fault displacement models. It is very difficult to develop this kind of models, largely because of large variability in the data. These charts and the ones in the next slide were put together by Brian Chu for principal displacement in the FDHI from strike slip events in the FDHI database. The small circles are measured displacement, and the curves are predicted medians and the 5th and 95th percentiles from Brian's new model. For each chart, displacement is plotted in log scale on the vertical axis against normalized position on the fault, or L to L. Now we see large variability in most of the events. Another striking feature is that the 5th percentile curve and the 95th percentile curves are not symmetrical about the median curve. So the data is skewed. These are for larger events. Variability is even more apparent, especially in landers, not so much in some other events. So there is also large variability from event to event. The new fault displacement models compared to the previously published models can model this kind of data distribution much better, and they can they also predict more reasonable displacement, especially for low probability levels, exceedance probability levels. This is an example data set for distributed displacement. It is plotted against the rupture distance. Now, distributed displacement is not a major part of this workshop, but Francesco Vicini will give a lightning talk on this subject. In summary, both PFDHA and the DFDHA use fault displacement models to estimate displacement. They both incorporate variability in displacement. The earthquake approach of PFDHA incorporates event rates and additional probability models, including probability of surface rupture given magnitude and probabilities of surface rupture crossing a site area due to gaps, step overs, etc., and uncertainty in the location of future surface rupture. Now, as I mentioned before, this workshop is mainly about fault displacement models for principal displacement. There's not much about these other probability terms, except a couple of lightning talks, and perhaps Steve will talk about it in his presentation of the example applications and the statewide fault displacement hazard map. Some examples of PSHA results are displacement hazard curves and displacement hazard maps, which would require detailed fault geometry. Thank you.
Very good. I appreciate Rui. Again, please save your questions and comments, enter them on the chat box, and at 11:25 a.m. Pacific time, we have a few minutes for questions and comments. So please enter your comments in the chat box, and Alex is going to save them. Next speaker is Professor Rob Moss, and Rob is going to talk about, again, probabilistic fault displacement hazard. Rob, welcome.
Thank you. Thanks, Rui. Rui did a good job of setting us up here. And I was tasked with talking about prior models. So that's models prior to the FDHI work. And as Rui mentioned, one of the best examples of a load-tested structure for fault displacement was the Trans-Alaska Pipeline. I was fortunate to be on the reconnaissance of this earthquake. And when we were allowed to first visit the site, we could observe the displacement, which is in the foreground there, and we could observe this load-tested structure. Wouldn't we all love to have this as part of our resume? We have a structure, we designed it for fault displacement, and we had a success. So this was in 2002, and I'm going to be stepping through the models from essentially 2003 to 2013. As Rui mentioned, the Young's et al. Model came out. A whole slew of authors were part of that work as part of the Yucca Mountain Project. I had been working on some models. The first one that we spit out was having to do with a tsunami-genic displacement forcing function. And then we went terrestrial. So these are reverse events or subduction events. Same time frame, Peterson et al. And their group came out with the model for strike slip. And then in Japan, Takao et al. And colleagues, they had a series of publications. The 2013 one was the one that set the stage. And they were looking at Japan-specific reverse and strike slip events. And so this was the lay of the land for essentially a decade. People wanting to do PFDHA, these were the models that were available. Notice that none of the models really complemented each other. There was just by type or by event. And so we didn't have multiple models to put onto a logic tree. During the same time frame, there was a number of workshops that were particularly useful in trying to get people coalesced around the ideas and the concepts. There was a peer fault hazard workshop in 2009 in Berkeley. there was a session at San Diego SSA on PFDHA, and so that kind of circled the wagons in 2011 with the models that were available at the time. And then several years later, there was a fault displacement hazard analysis workshop put on by the USGS. And so what I'm going to do is I'm going to compare and contrast the models up through that 2013 timeframe. And one of the main goals of doing PFDHA is to come up with a hazard curve. And here our hazard curve on the x-axis has displacement. And Rui discussed the the full integration to get that hazard curve. But what we're doing is we're multiplying a bunch of probability distributions. And when you multiply a bunch of probability distributions, it approaches the log normal. And so what we're looking at is we're looking at the cumulative log normal distribution. We're taking the complement of that, and then we're multiplying it by a mean annual rate, and that gives us our hazard curve. And one of the items for discussion that we may not dwell on too much in this workshop, but what is an acceptable level of hazard when we're talking about fault displacements? And this is still kind of the Wild West at this point, but it's a point that I think that we need to be thinking about and discussing as we move forward. Here I'm showing some principal and distributed displacements. This was from the Yucca Mountain work. And the base model components that we see in PFDHA is that there's a probability of surface rupture given submagnitude. And as Rui mentioned, there's a lot of variability. This particular probability distribution could have a huge impact on the hazard curves. And then we have magnitude versus displacement relationships. And then we have normalized displacement with distance. And this could be along strike, or this could be off of strike. So we could be talking about principal or distributed displacements. So the probability of surface rupture, this was first introduced in the Young's et al. Model, and you can see the variability there depending on how you parse the data and what data you're looking at. And we're essentially using a logistic regression to resolve this. Was it or was it not observed given the magnitude? The work that Zach Ross and I did, we collected some more data and we focused on reverse specific. And you can see that reverse compared to other mechanisms tends to be on the lower end in terms of if we're going to have surface rupture given a particular magnitude. And here I'm showing the Takao work where they also were doing the same with some additional data. Now we move to the normalized displacement. And this could be, this is principal, and we're going to be talking about along strike X over L, or for Peterson, that's I over L. So here we're looking at the normalized displacement, and we can normalize it by the maximum or average displacement. And the normal events that were available to Young's et al. Was 11. And you can see the scatter in the data there. For our reverse model, we had 9 events that we could aggregate and look at the data. And then Takao had essentially 19 events. And the distributions that have been fit to this, gamma, Weibel, and beta distributions, are often flexible enough to capture the central tendency and the dispersion of this data in terms of projecting it forward. And here I'm showing the Peterson et al., where they had 21 strike slip events, and they did a bilinear fit to this data. Now we move to the component of the models, which is the maximum or average displacement with respect to magnitude. Young's used a Wells and Coppersmith approach. For our model, we augmented it with some more reverse events, and you can see the comparison between Wells and Coppersmith and the events that we added in our regression analysis. And what we're trying to come up with is a probability of displacement. Here I'm showing X over L of 0.25, so that's a quarter along the rupture. The middle of the rupture is an X over L of 0.5, and the end of the rupture would be 0. We usually fold the earthquake in half, and we aggregate the data, unless we treat it as non-symmetric. So this is showing what was used in Young's, and this is showing what was used in the Moss and Ross 2011. Here's Takau's approach. They had a different database. And then here's what was used in Peterson et al. So each of these components up to this point varied depending on the mechanism and very depending on the modeler's choice of how to approach the data. I'm going to touch on distributed displacements because that ends up being one of the key components for doing PFDHA when we're off of the fault, so when we're not dealing with lifelines that cross the fault. The Young's approach had two components. One is the probability of distributed, and the other one is a normalized distributed, so a scaling. And you can see that they've broken it out on a hanging wall and footwall for the normal events. On the right, you can see that there was not a lot of data to deal with at that point. The benefit of FDHI is that we've aggregated as much data available to us now, and so we have much improved models because of the increase in data. This is Takau's approach, very similar. Probability on the left and a scaling on the right. Again, they broke it out into hanging wall and footwall. They're dealing with reverse and strike slip. So they put reverse and strike slip into the same bin. And then Peterson's approach, probability on the left and the scaling on the right. The reverse model that Zach Ross and I kicked out, we did not address distributed. We were just looking at fault crossing at that time. So what we want to end up with is hazard curves. This was a recent study where Test et al. Applied the Young's model for normal events, and they're showing how the hazard curves step out as a function of distance from principal faulting, and they're also showing it with respect to some different hazard levels. And so for me, this is the visual that I like when I think about these type of projects, where maybe we have a facility and the facility might have some lifelines that cross the fault, and then it might have some features that are away from the fault. And this gives you a complete picture. So what we see is principal, oh, sorry, not principal on this. We have 100 meters out to 2 kilometers, and then we show X over L from just a little bit in from the end all the way to the middle. 0.5 is the middle of the fault. So this gives us a nice relationship to where I think this is where I would like to see projects head, is to evaluate it this way, but it also depends on the project. Hazard mapping, as has been alluded to, is something that's coming. And this is a recent project that I just finished with Jan Gavio in Montana, and we're looking at the Bitterroot Fault, and we're trying to come up with some very rough diagnostic. And so at the large mapping scale, we delineate a 1 kilometer wide hazard zone, and then the inset shows estimates of displacement exceedance for this normal fault, where most of the displacement is on the hanging wall side or the valley side. This is a preliminary, but in my head, this is what I see as a useful tool for agencies, stakeholders, and others to try to visualize what the hazard might be and then how to address that hazard. One thing that I do want to spend a little bit of time on at the end of my slides here is fragility. So we've only been talking about loading, and the other side is the resistance. And so the resistance or the fragility is something that I think hasn't gotten enough lip service. And there's been a number of individuals involved in submitting proposals for the next ASCE 7. I've been working with Nick Odell a little bit on this, and here we're trying to come up with what is the acceptable, allowable fault displacement resistance that structures can be designed for with and without special considerations. And so here's just some preliminary stuff. There's others that are working on complementary or friendly proposals that hopefully in the next 6 to 8 months will be merged so that we can move forward and get something in the next round of code revisions. But that fragility, what can the structure withstand, is something that I think needs to be more on the forefront of the discussion. Clients will say, hey, give me the probabilistic fault displacement hazard curves, and you give it to them, and then you say, well, okay, but what can your structure handle? And then often what you see is blank stares. And so back to the day when we were dealing with ground shaking and we talked about loading, and then we examined the fragility of structures for ground shaking. That's the phase that we're at now, is we're doing okay on estimating the loading for fault displacements. There's a lot more uncertainty, but we're moving forward on that. And on the other end, we need to think about, well, what is the fragility and the resistance of structures to these displacements? Here, I was only looking at vertical displacements. And again, this is preliminary work. The proposals are getting vetted and analyzed and merged at this point. But I think that this is an important topic that we need to keep in mind when we're talking about fault displacement hazard and probabilistic PFDHA. And that is the end of my slideshow.
Great. Thank you, Rob. Appreciate that. Again, keep your questions and comments and enter them into the chat box, and we'll get to them during the question and answer session at 11:25 a.m. Pacific time. So next is Alex, and Alex is going to give you an overview of the database, which has been extensive and is publicly available. Alex, welcome.
Yes, hello everyone. So first, thanks so much to Dr. Chen and Dr. Moss for essentially summarizing what is about 25 years of fault displacement hazard analysis in less than half an hour. They've managed to bring us right to the doorstep of the FDHI project. And so that's a great segue into the rest of the talks for this, this workshop series. And I'll go ahead and start sharing my screen here. Maybe. Did I fail? I practiced this earlier. Oh, my goodness. Alrighty, I think I'm sharing. How's it look? Yeah, I got a thumbs up. Perfect. Okay, so today, well, my name is Alex Sarmiento, and today I will give an overview of the new database that we developed for the Fault Displacement Hazard Initiative project. And this work was a very large community-based effort with major contributions from our team here of geologists, engineers, and model developers. Go ahead and put my pointer on. There we go. So our main goal for the database was to develop a standardized collection of fault rupture and fault displacement data and related metadata. And we wanted to do this in a way that supports the development of these new empirical fault displacement models. And so that means the content of the database was heavily driven by the needs of the model developers. And so in addition to just the raw data of rupture traces and displacement measurements, we developed a pretty comprehensive collection of metadata to go along with that core information. And then there are, of course, a handful of data sets and databases like this already out there, but they have various limitations. They may be outdated, or they lack geospatial control, only for one style of faulting, or in a lot of cases, not even publicly available. And so we wanted to also address some of those limitations here in this new database. So we collected the data through a literature review. We did not go out and collect the measurements ourselves, but instead we drew from the reliable scientific literature. And all of the data went through a very extensive quality review process where we systematically looked at everything for completeness and accuracy and consistency and whatnot. We had a few key requirements for the events and the data sets. We focused on historical shallow crustal surface rupture and earthquakes. That's all that we considered for the database. And we required geospatial control, not just for the measurement locations, but for the full map of rupture traces. And so this means there are some earthquakes that are not included. The earthquakes that did not rupture the ground surface will not be in this database. And the kind of summary statistic data sets that give average displacement or maximum displacement, those are also not in this database because they lack the geospatial and related information. And similarly, the slip profiles or empirical displacement profiles also lack geospatial control and are not included. So as Dr. Berzonia mentioned at the outset, there are 75 earthquakes in the database, spanning magnitude 4.9 to 8. A little under half are strike slip, a little over a third are reverse, and only a fifth are normal. And so the normal subset is certainly the smallest and is pretty well clustered around magnitude 7. These histograms show the distribution of the number of events based on magnitude for each style of faulting. And so normal is pretty well consolidated here around magnitude 7, whereas reverse has the widest span going from the 4.9 actually to 8. And there are over 40,000 individual measurements of fault displacement in the database. So Dr. Chen and Dr. Moss both touched on this earlier, but most of these models treat principal and distributed faulting separately because the data and the driving mechanisms are sufficiently different. So the conventional definitions are, we say the principal ruptures are those that are the surface projection of the fault plane that ruptured at depth and caused the earthquake. And then distributed ruptures are those other secondary faults, splays, and shears. And so to kind of keep with the tradition for the models that treat these separately, we applied this classification to all of the ruptures and all of the measurements in the database. We also have geologic information and topographic information for the sites and ruptures in the database. We have lithologic descriptions derived from regional geologic maps using your standard geospatial processing techniques. And then we've taken the lithologic description and broken it into some simplified geologic units, bedrock, and then 3 different types of alluvium. And we also have elevation data and several pre-computed common terrain metrics like geomorphic terrain class, terrain ruggedness, and several others. We also provide estimates for net displacement for all of the measurement sites in the database. I say estimate because net displacement usually isn't measured. And so there are some limitations with these estimates. The net displacement, when it's not provided, we calculate it from the components that are measured at the site. And then usually it is the lateral or vertical component that's measured. Very commonly just one component, but also there are many cases where we have both the lateral and the vertical component reported. What is really missing in a lot of cases, a lot of sites and a lot of events is that heave component, that fault normal displacement that is, or a dip slip component, that either opening or compression, that dimension is missing and it's rarely measured, it's not usually reported. And so that means when we calculate the net displacements in the database, that heave or fault normal component is missing in a lot of cases, and the net is really the resultant of a lateral and a vertical displacement. I mention that because it's going to come up, I think perhaps in Steve's talk and certainly on Wednesday and Friday. So planting the seed a little bit for further discussions on that. And then finally, of course, we require geospatial control for everything. So we have geographic coordinates for all of the rupture traces and all of the displacement measurement sites. But we also have a unique coordinate system for each earthquake that gives a launch strike and a strike normal distance metric for each earthquake. And this is really useful because most models use these as predictor variables, that length along the rupture, the X over L or L over L, and then distance from principal rupture in the distributed models. These are commonly used. And so we have these coordinates, the geographic and the event specific system coordinates for all of the ruptures and measurements in the database. And then the easiest way to kind of use that as an end user is you can make nice slip profiles of the events in the database. So the database is available for free and easy download. I will paste the links in the, how do you call it, in the chat box after my talk here. But you can go to the UCLA Dataverse, which is a permanent open access repository, and download the database. It's in a couple of different formats, the conventional flat file format, but we also have a geospatial format, shapefiles and KMZs. We've very carefully documented all of the work that went into compiling the data and developing the metadata. And you can read about that in the technical report published by UCLA. That's free to download. And we also have a journal article that has been published like as a preprint in Earthquake Spectra's special collection issue on fault displacement hazard analysis. So then here in summary, the FDHI database provides a standardized collection of fault displacement and surface rupture data and metadata. And the metadata were developed in a consistent manner for each earthquake with input from the model developers on what they needed. And so this really is the largest database of this type with not just the geospatial control, but the extensive collection of metadata. And it is freely available for everyone the community to use. And that's it.
Very good. Thank you very much, Alex. As always, Alex has been really the driving force behind the whole project. Thank you, thank you, thank you. As Alex mentioned, there will be a special issue of Journal of Earthquake Spectra, ERI Earthquake Spectra. All the papers back to back will be published in a special issue. However, we are not going to wait for all papers to be ready to publish the special issue. All papers are that are accepted are published online, but then the print will come all of them together. All right. Alex also entered the database link. You can download the database and the report and everything else online. We are 3-4 minutes ahead of time. My suggestion is that let's have a break and come back at 11:05. In other words, 9 minutes from now, 11:05 Pacific time. Let's have a few minutes break. We'll come back, and after that, we are going to hear from Fia, Steve Thompson, and the discussion. 8 minutes or 9 minutes break. 11:05 Pacific time. Thank you, thank you, thank you. Very good. Let's start. So the next speaker is Fia, and she's going to talk about the ranking in the shared database, which is important issue. Fia, welcome.
Thank you. Thank you, Yusuf. I will share my presentation. Can you see it okay?
Yes.
Okay, perfect. So my name is Fia Nurminen, and I present here today another empirical database developed for fault displacement hazard purposes. The database work in general follows the same principles Alex already presented in her presentation, but there's one very big difference in SURE database, and this is fault ranking. As already mentioned in the previous presentations of today by Dr. Chen and others, in BFDHA, principal faulting is taken separately from distributed rupturing. And in SURE database, we take that idea a little bit further, and we distinguish various types of distributed rupturing as we see from the empirical data. So in SURE database, we have 50 earthquakes of all main kinematics, 16 strike slip, 18 normal, and 16 reverse earthquakes. In the database, there are more than 75,000 surface rupture traces and about 19,000 points of displacement. And each of these has a ranking applied to them, and every point is associated to corresponding rupture trace. In the simplest kind of a case, this is similar to the seen already in the previous presentations today. So we have principal fault rupture that is usually the easiest to recognize from mapped surface data. It has high continuity, and usually the displacements are seen along the principal fault. In addition to that, we have distributed rupturing around it. And in SURE database, this kind of simple distributed rupturing contains all the, let's say, general of fault rupturing with no other, no reason to rank it otherwise. However, we can see from various earthquake data that reality is not always so simple as in the previous case, but we have other types of distributed rupturing that behave differently, and they occur, their occurrence is guided by different factors. First of all, I show two examples here. First of all, so-called primary distributed rupturing, which is basically, by which we mean rupturing along splays or other structures that we can assume being connected to the principal fault in depth. Usually these kind of structures produce rather continuous surface rupture trace of their own, and they can even cause distributed rupturing of their own. Then another case related to pre-existing or previously known faults is when an earthquake triggers rupturing along another fault within even tens of kilometers distance from the fault. These faults probably they can be or cannot be connected to the principal fault per se, but the movement along the principal fault of the earthquake in question may trigger faulting along these kind of structures. In addition to these, in our database, we have also a few cases in which we can recognize a distributed faulting related to large-scale folding caused by reverse faulting principal fault. These are examples of these are a bending moment rupturing and flexural slip rupturing that are both very site-specific and very local phenomena. Like their existence is strictly connected to folding in general. So in Shear Database, we came up with this very synthesized ranking scheme that is applied to all main kinematics in the database. And we can see that separating these is a reasonable alternative, at least in PFDHA purposes, as their behavior, their statistical behavior of various types of distributed rupturing seems different in our studies. Francesco will present on Wednesday an example of the results, like using this type of data in practice. And I leave here the links for the both the database and the articles that describe the database and the ranking scheme more in detail. Thank you.
Very good. Thank you. Thank you. Appreciate that. All right. Let's go to Steve Thompson, and Steve is going to talk about displacement metrics and definitions. Steve, welcome.
Great, thank you. Okay, are my slides up?
Yes.
Great. So I will go through some of the different definitions that the new fault displacement models use for displacement and some of the different displacement metrics that are used by the different modeling groups. And so this talk is really a continuation of Alex's talk earlier that went through the database. This is a little bit of a bridge to tomorrow's discussion of the models. So in the next few minutes, I'll be going through some just more examples of ruptures and some examples of the displacement data that are available to us. Then we'll look at some of the fault displacement model metrics that are based on the different ruptures that are involved in the definition of displacement, so how different ruptures are grouped. And then I'll pick up on a theme that Alex introduced, which is the different displacement components. The different displacement components that we know are happening in nature versus the ones that are preserved and the ones that we can measure and incorporate in our models. And then I'll go through a summary table showing the different previous published models that Rob covered, but also the new models we'll hear more about tomorrow and sort of how they use these different displacement definitions and metrics. And then I'll end on some conclusions and recommendations. So here, just again, more examples of surface fault rupture patterns that are recorded following large earthquakes. This is from an electronic supplement in Peterson et al. And we'll be looking specifically in the next slide at a portion of the Hector mine rupture. So here we have another example, one of the figures in the electronic supplement of Peterson et al. That highlights the difference between the principal ruptures and the distributed ruptures. And so we can see from the map in red, the long through-going rupture, other scattered distributed ruptures along it. Fia gave a great example how in the Schur scheme, they might be differentiating some of the longer and more continuous distributed ruptures from the shorter and more random and less continuous distributed ruptures. In the Peterson et al. Scheme, which is being continued for the FDHI database scheme, we're grouping all of these together as all distributed ruptures. For the principal rupture, again, it really distinguishes itself in many, many cases based on the longer, more continuous through-going trace, as well as the larger displacements. And so here in the figure, we see both the recorded lateral or strike slip. So these are the SS measurements in centimeters. In this reach of the Hector mine rupture, these are multi-meter principal displacements. they really distinguish themselves from the amounts of displacement that are measured on those distributed ruptures that are on the order of 10% or less, kind of on average in the strike slip database scheme. So, and as Fia just went through, there are alternative classifications available. There are other displacement prediction models, fault displacement models that are based on these alternative classifications. So just be aware that there are different ways to define and group ruptures. So the next few slides, we're going to look at some of the different definitions of displacement, some of those different intensity measures that are coming out in the new models and how they compare to the previously published models. So here in the main part of the map, we have the continuous rupture traces, red for principal, blue for distributed, and then the circles represent point measurements from whatever field data collection team was involved. And so the classic metric for principal displacement hazard that we have grown accustomed to, that is the basis for the previously published models, is that we define some sort of reference line along the trend of the rupture. Alex introduced this as according to the kind of event-specific coordinate system. And so this gives us a reference line, and any measurement of principal displacement that can be projected onto that reference line. And that is the data that goes into those fault displacement models that are predicting principal, or sometimes we've been calling it single principal displacements. One of the innovations of the new FDHI models that we'll hear about tomorrow is there are some different ways to group the data, to group the ruptures, and those include a sum of principal and an aggregate displacement measure. And so for these, different modeling groups have come up with different concepts to have what essentially can be thought of as a zone or a window that can go along the X over L reference line. And within those windows, the sum of principal is basically the sum of measured principal displacements within that window, or the aggregate displacement measure is one where we sum not only the principal, but also all of the available measurements along distributed ruptures as well. And so one of the important things to recognize just in this scheme is that it is the sums of all the displacements that are measured, and there include, particularly in distributed ruptures, there are many shorter, more random distributed ruptures where no displacement measurements have been made in the field. And so the aggregate measure is still kind of a limiting measure of the true sum of all the on-fault displacement. So to finish out the concept of the different displacement measures that are in currently available fault displacement models and perhaps in future fault displacement models, I'm showing another example here of the type of data that are just becoming available to us. And so the yellow is supposed to represent a measure of the total fault zone deformation that includes both the discrete on-fault component, but also a distributed off-fault component of deformation. A lot of you are familiar with Chris Milner's work and some other work during COSI core and other types of image correlation methods. There'll be a lightning talk tomorrow, I believe, that Chris will give on the work that they're publishing in Earthquake Spectra, where they're introducing a database for several strike slip ruptures where they're able to give us this total fault zone displacement measurement. We don't have them now, but in the coming years, we anticipate to have other types of fault displacement models that'll give us insight into total deformation. And then for completeness, there are also models for distributed displacement hazard. Francesco will give a lightning talk on one before. Rob touched on these. And the distributed models are most similar to the single principal displacement models. Okay. The other concept, this is picking up where Alex left off, and this is looking at the displacement components. As we know, the ideal case would be that we would measure the full net displacement, and we'd come away with measurements of all of the different slip components. So we would understand the lateral components, fault normal, horizontal, or heave, and the vertical. But the realistic case in the data that goes into the database that we're able to model is that we can only measure and then we can only record what survives and what's interpretable. So having a fence as an offset marker is an ideal case that very infrequently occurs, and we have to recognize the incompleteness of kind of a messy data set. And so here we'll show a few examples. Now we'll switch to a 2D view where we're looking at a reverse offset example. So again, in an ideal case, we'd be able to directly measure that dip slip component. We would have a way to observe the near surface fault dip and perhaps even that rake component, that obliquity component represented by lambda here. But what is the typical case that happens in nature is we have unconsolidated or semi-consolidated deposits at the surface, and so we get immediate scarp collapse. And so that whole dip slip displacement, the evidence for that does not survive through the earthquake, and we are only able to measure what is surviving and what's interpretable. So for the reverse fault case, this is dominantly that vertical V component shown here. And that other information that we really want to have about the fault normal component, that's missing. The information for that is buried in this case, and so isn't easily recoverable in a post-earthquake fault investigation. So as Alex mentioned, the FDHI database is very rich in measures of vertical displacement and in that strike slip or lateral displacement, but only in very few cases do we have well-recorded dip slip or fault normal displacements or direct measurements of that fault dip and rake. So the FDHI database, it does include a measure of net displacement, but as Alex started to mention, that displacement is based on all of the reported data. And so in a lot of the discussions that we're having, we've started to call this net star displacement to distinguish it from the true 3D net displacement. And additional information is needed when we implement these models in order to estimate a true net displacement. So it's outside of the new fault displacement models. And this inset diagram that's right here just shows for this 2D case, if our real objective is to understand the dip slip displacement, FDHI will give us a reliable estimate of the vertical, and we need to use site-specific or some other information to get at that dip component. And so in the new fault displacement models we'll hear about tomorrow, the model teams have selected either this net star or the vertical component as the displacement measure. The previously published models mostly used mostly the lateral component or the vertical component. As Alex mentioned, one of the unique and really wonderful aspects of the FDHI database is the detail of the documentation. And a lot of that detail is really lacking as what was the basis for some of those previously published models. And then down here are some examples of the conversions that we will need to do if the objective of a project is to determine net displacement, where we need to divide either the net star by the sign of the dip, or in the case where vertical is the displacement measure, we need to divide by both the sign of the dip and the sign of the rake. So this table gives us a summary. It's a little bit of a look ahead to the talks we'll hear tomorrow, where the new fault displacement models under the FDHI project are shown above this dashed line. We have the Cho et al., the Kuhn et al., Lavrantiadis and Abrahamson, and the Moss et al. Model. For the Cho et al. Model, it just covers strike slip faulting. The Kuhn and Lavrantiadis and Abrahamson cover all styles of faulting. and the Moss model, which is an update of the Moss and Ross 11, is just focused on reverse faulting. And so those groupings that we looked at a few slides ago, the Cho and the Lavrantiadis and Abrahamson, they have versions where they're looking at some strategies to come up with a sum of principal displacement measurements. The Kuhn et al. And another version of the Lavrantiadis and Abrahamson model, they include an aggregate, or they solve for an aggregate displacement measure. In the Moss et al. Model, we solve for the more traditional, just single principal displacement measure. Those displacement components, these modeling groups are all using that net star displacement measure because the Moss model was really just focused on reverse faulting, where that fault normal component is very important. We chose to just go with the vertical displacement measure. Some of the last things we share in this model are these other more fundamental basic metrics to the different modeling groups. We're solving for principal displacement D, but some of these models also provide ways to measure the average displacement AD and or the maximum displacement MD. And as Rob alluded to, and Rui as well, there are both models that solve for D as a direct function of both magnitude and normalized distance along strike, but they're also normalized principal displacement models where we solve for the normalized displacement D over AD or D over MD. And then some of the nomenclature that you might see tomorrow or you might see in the near future of how we distinguish and abbreviate these terms is shown in that right column. Okay, and then my last slide. So conclusions, the different fault displacement models, the models and the model teams, they have made different choices about which displacement metrics they use. And as we'll see tomorrow, some different methods for evaluating the data. But important for implementing these models, adjustments to the fault displacement models may be necessary if calculating true net displacement is a project goal. And that's largely due to the incompleteness of the empirical data, which we have available. And then lastly, an important recommendation, when using these models, do not assume that alternative fault displacement models can be treated as epistemic alternatives in a logic tree. So do not necessarily take all of the available strike slip models, assume that those can be treated as epistemic alternatives under your displacement exceedance part, and then go ahead and compute some sort of weighted mean. These models that are based on different metrics, they really may be addressing different questions that are independent or that are unique to questions that you could ask for any given specific project. And we'll try to cover more of that in some examples we'll present on day 3. Okay, I think that's it. Thank you.
Very good. Appreciate it, Steve. Thank you. Thank you. So I'll pass it now to Alex to coordinate the discussions and the questions. Alex is with you now.
All righty. Great. Thanks so much. First off, thank you, Steve, for setting the stage for what we will need to talk more about on Wednesday and Friday, which brings up a good point. I want to remind everyone that day 2 of this workshop series will be on Wednesday, not tomorrow. So we'll mention that at the end. But when Steve says tomorrow, he means Wednesday. It's okay. So we have a couple of questions in the chat. We'll go ahead and answer those here, and then I think we can open up the floor for some other questions. So the first question from Harold is the reported total slip being resolved into coseismic slip and after slip? So I think this is a database question related to your second question, if that's right. And Harold, if you'd like, you're welcome to hop on the microphone and discuss more.
Okay, sure. For example, in the case of Superstition Hills earthquake, the afterslip pretty much doubled the co-seismic slip. So the date on which the slip measurements were made matters in determining how much slip you got. And the papers that you probably used to build the database include a fit to how the afterslip grew through time. And so I just wondered, are events like Superstition Hills flagged for the occurrence of afterslip?
Yes, so the Superstition Hills in the 1979 Imperial Valley, of course, are great examples where you had teams of geologists that went out over not just the days after the earthquake, but weeks or months, or even in some cases a year later, to understand how afterslip kind of grows with time. And so we actually have, when that information is available, we have all of those measurements in the database, and they're time-stamped, and they have a unique identifier. And so the model developers, I think we have recommended that they use the earliest measurement of slip that available to try to avoid the effects of afterslip. But you have this problem in all data sets where if there's a chunk of time between when the earthquake occurs and folks get out there to measure it, some amount of afterslip is kind of inherently in the data. And we capture that when we can, but that's a common thread in all of the data. Maybe an interesting point, we've talked about this a little bit early on, is so the most of the afterslip we think occurs, kind of in the short term, the hours, days, and weeks after the earthquake. And something that kind of came up is, well, in a sense, there are a lot of structures that care about the total slip that occurs, whether it occurs that instant or a little more accumulates in 5 minutes. It might not matter. The structure still feels it. So that's kind of a long answer, hopefully, to your question.
Okay, thank you.
Yeah, thanks. That was a great question.
And then the second question was, of course, there's cases of triggered slip where a fault near the causative fault gets shaken and then has some slip on there that could affect infrastructure. And so it seems like important to include cases of triggered slip. So I'm just wondering if triggered slip is included in the database.
Yeah, so the spatially proximal, that's kind of a very non-specific phrase, but the nearby measurements that maybe were on adjacent faults that are part of the system that did experience some distributed deformation would be in there. So maybe some of the Norcia cases would be a good example. But on the flip side, if you're thinking of the Elmire Kukapa earthquake, there were triggered slips 50, 80 kilometers away. We did not include those. That seemed to be outside of the range of I don't know how you even start to build a model for an earthquake on a fault 100 kilometers away triggering a centimeter of displacement. So in that case, that's not in the database.
Okay, thank you.
Yeah, thanks so much for your questions. All righty. Let's see if questions are coming in. This is great. Dr. Idris. You know what? Tim Stahl got one ahead of Dr. Idris. So Dr. Stahl, let's see. You're welcome to hop on and ask your question, or I can read it.
Yeah, thanks, Alex. I think Rob has answered it in the chat, but do we have the equivalent of an FDHI database for fragilities and impacts, a way of standardizing those observations and then translating that to practice seems like it would be an important priority.
Yes, but we need to have a workshop to do that. I'm not aware of any database that's out there. It's kind of hidden in different areas, and I think that in the next year or so, we should have a workshop on fragilities related to fault displacements.
Let me make a comment on that. Rob is correct. I think in the entire earthquake science and engineering that we start from hazard, then we go to simulations, then we go to fragility, then we go to the consequences. Fragility is the least advanced package, and the reason is very simple. Is very labor intensive. So as part of another large project funded by California Energy Commission, PG&E, and SoCalGas, we developed a fragility database for transmission gas pipelines. I think it's the largest database of fragility for the natural gas transmission pipelines. And still we are making it larger and larger. And in the next couple of years, we are going to make it available to the public. But that's only for natural gas transmission pipelines, not for other structures and so on. We need a very large community-based data project to put together for fragility.
It's structure dependent.
Exactly.
You can't have a generalized fragility, have a generalized fragility approach.
Exactly.
Not generalized fragility curves.
Exactly. And for example, Professor Idris is absolutely correct for even transmission natural gas pipeline, which is one specific. We have over 500,000 different combinations. The size of the pipeline, the angle of the fault with respect to pipeline pressure, is a structure specific. So it's very labor intensive, but we need to do a better job as a company. Alex, sorry.
Okay. No, that was great. Thank you so much. And so that's handles the fragilities question. And then Dr. Idris has a couple of questions. And I think you answered this in the chat, Rob, but we'll just let the discussion maybe happen here a little bit. Dr. Idris, did you want to go ahead and?
Is why? I know the statement. That's a statement, that's not really an answer. Is that why did you limit it to 2013? There's nothing available, or just this is what you decided to do?
There wasn't any newer models. So there was a span of about a decade. Takao and colleagues were working on improving their model, but it essentially wasn't a new model. They have 2014 and 2016 publications, and it was just one was doing hazards for particular case studies, and the other one was using a Bayesian approach of including uncertainty. But past 2013 till now, there was essentially no new PFDHA models that I'm aware of, and there wasn't anything in use other than the ones that I presented.
Anyone else is aware?
This is Steve. There have been a few other efforts, mostly out of Europe. So there's a Ferrario and Livio model that addresses distributed displacement hazard. FIA and colleagues produced a model that also was for distributed displacement hazard. But as far as the main models that we tend to use in engineering practice, Rob covered them. And so there really has been a large gap in time between, like Rob said, around 2011, 2013 until recently.
That's a span of 12 years. It's very surprising.
Yep.
And with the 2013 timestamp, that's for the probability of surface rupture model. And so there's so many different ingredients in the PUFTA integral. As you know, it feels more complicated than the PISA. And so there's different groups focusing on different modeling aspects, of the integral. And our work here has primarily focused on that exceedance term, right? The probability of the displacement probability distribution for principal type ruptures. And so that's a little bit of Ali's question was, are these models going to answer the question of distributed displacement? And the new FDHI models are generally focused in this stage on principal or aggregate or sum of principal displacement, and that'll be a future phase of work.
As Alex said, we have a dream that we do phase 2 of Fault Displacement Hazard Initiative. Maybe it's a smaller phase, but there are still a couple of things, including the distributed faulting, that we really like to answer because of practical importance.
The model that was published last year by my apologies for mispronouncing his name, Levin Delatis and Abramson, is not considered a probabilistic model?
Oh no, it is. It gives you your probability displacement probability distribution, but it's for that aggregate metric and the principal sum of principal metric that Steve talked about. So it doesn't specifically give you distributed displacement amplitude, and there is an element of a probability of surface rupture in there that is related to the probability that you have zero displacement at your site, but that's not the classical probability of surface rupture model that's Rui and Rob talked about, that probability that your earthquake produces surface rupture anywhere. That's a separate part of the integral, right? You have the probability that the earthquake itself produces surface rupture, and then you worry about whether that surface rupture happens at your site. And so that 2013 model was does the event itself make a surface rupture?
Very intriguing twist on this. I have to look into that a little more carefully. That's a very interesting observation.
And by the way, Professor Idris, that paper by Greg and Norm is part of FDHI. As I mentioned,
yeah, and he's a co-convener.
Yes, exactly.
I'm just out of curiosity. I get involved in these issues every once in a while, not on a continuous basis. So I try to stay up to date on it, and I was a little surprised that that's all we have in 2013. Where actually we used that model last year on a major project in Los Angeles, the most recent one. So
okay.
Absolutely, Alex.
Very, very interesting. But I loved your. This is Alex. I loved your twist on it. It was very, very fascinating. Thank you.
Yeah, and actually, I think you had one more.
I have to come to UCLA to meet you.
Yes.
You're welcome anytime.
And I think, Dr. Idris, you actually had one more question that I think Steve is chomping at the bit to answer. Are you suggesting we underestimate the displacement in reverse earthquakes?
I was intrigued by that, by your presentation. Are we underestimating it? It's just a question. I have no idea what.
Yeah, no, that brings home. That's a great question, and I think our current view is that when we have been using Moss and Ross, and to some extent when we've been using Young's et al., when we think about the data that were used to constrain those models, it's likely that that fault normal component was underestimated or was practically not included at all. And so we consider best practice right now to be factoring in kind of a conservative assumption that that is just the vertical component. And if we're interested in the net component for some of these models, we should be considering adding back in that contribution to net from a site-specific dip uncertainty, and then depending on the project, looking at rake uncertainty as well. So looking at a possible lateral component. So I don't want to say this categorically, but I think best practice going forward is to really pay attention to what is that, what are the components that are part of that displacement that's being predicted, and then how do we properly adjust.
Thank you. Very, very valuable information.
Yes. All right, thanks. And actually, I think I misread the comment as probability, or your earlier comment, Dr. Idris, says probability as PSR, and you meant general probability models. So I'm sorry. Everyone tried to jump in and rescue me, but I doubled down on reading it wrong. Sorry about that. So hopefully we've answered your questions. The question from Ali on distributed displacements. As we mentioned, the new models at this point do not treat that directly, but future work will. And that's a little bit related to, I think, Yunshin's question. So when these models, they predict aggregate displacement or sum of principal, that hazard curve is for that metric. There's not really a way to deaggregate it into the distributed or the principal or the individual contributions at this time. And so the kind of the future work, which I think Dr. Lavrentiadis is working on now, is taking his aggregate displacement model and making a compatible and an agreeable model for distributed displacement. So that would be the step forward, is to make sure that the models work together. I think, let's see, does that answer your question, Yinxing? And if you can, actually, I'm sorry, you can go ahead and unmute and talk if you'd like to ask more.
Thank you for, yes, that answers my question. Thank you.
Yeah, perfect, thank you.
Very good.
I think we're at the end of the questions.
Any other question or comments from audience? You can turn on your mic and speak. We still have a few more minutes.
Well, it looks like there's one more question here. The difference in distribution between style of faulting. Did you want to jump on, Matt, and elaborate on what you mean by distribution? Oh, you might be muted if you're trying to talk, Matt McMacken, excuse me.
So either Alex or Rui, you want to show your slide about the difference in distribution between the strike slip and so on?
Yeah, trying to mute. Yeah, let's see if I can help you here. Tried to ask you to unmute, Matt, but the Zoom gods are being stubborn today. Yeah, so I guess I'm not sure distribution. I don't know if you mean the
Distribution
slip
in
amplitude
a database or the difference, yeah, predicted difference.
Yeah.
So there are two different things. Distribution in a database, Alex showed less than about 50% is a strike slip, a little bit less than that for reverse, a little bit less than that for normal. For the contrast between the predictive values between reverse and strike slip and normal, we will have a good presentation on Friday when Alex is going to show the difference between different models. Or Wednesday, each modeler, they show their models. They show the difference between, for example, reverse versus strike slip.
Simply the number of different types of, excellent. So there's a little under half of the earthquakes in the FDHI database are strike slip, about a fifth are normal, and a little over a third are reverse. So that shakes out to, I think there's 14 normal earthquakes, and I can pull up my slides maybe and give you the exact numbers. But, oh gosh, where's the slide?
35.
Yeah, so 35 earthquakes are strike slip. Yeah, thanks. 35 are strike slip. 25 are reverse oblique, and 15 are normal. Yeah, thanks. Alrighty. And
Very
then
good.
for FIA, is FIA still here? It's very late in Europe. See if I don't want to speak out of turn here.
Europe, which is late.
Yeah, FIA's still here. So there's a question for you, FIA, on what do you assume that rank 1.5 distributed faulting are connected at depth to the primary rupture. Based on what did you assume? And Fia, you are muted if you're trying to answer. Right. Well, I don't want to speak out of turn, but I think the second link, the updated database, the Nurminen et al. 2020, I think was the year. She talks about that in there. I can paste the link in the chat, and we can also track this question for you, Maddie, and we'll get back to you.
It's very late in Europe where Fia is lives.
Yeah. So.
Yeah, can you hear me?
Oh, very good.
Oh, we see Lisa. Yeah, we have Lisa, another colleague. Yeah.
Answer to this question. It's based on the reference, the bibliography. So if they are connected for field camp data, you know that the fault are connected, so it's 1.5. Is this the answer to the question? Okay.
Properly?
Can you hear me?
Yeah, now I can hear you.
So Lisa, one more time, please.
Yeah, it's based on the bibliography from the field camp data. So on the field trip, you know, or based on the geological map, you know that the fault is connected to the principal fault. And so you can tell that is a 1.5 ranking.
Okay, so if it's connected at the surface in geological maps?
Not at the surface, but they are not the same, are connected to the principal at the depth.
Okay.
Can I add something? This is Paolo.
Oh, okay.
Sure.
Yeah, Lisa is correct. If you have information from the literature from aftershock distribution that the secondary fault is connected to the principal fault, this is one point to rank the rupture as 1.5. But there is another point, rank 1.5 distributed rupture occur on faults which have geologic or geomorphic evidence of past ruptures. So, for example, a rupture on a pre-existing fault scarp, suggesting that you had the previous surface rupture. So something that you can map before the earthquake. So a secondary fault, but that you can map before the event, in theory, because you have offset of geologic markers, pre-existing scarps that you can map on the topography. So we checked, we observed the ruptures, and then we checked if there are information of pre-event geologic or geomorphic evidence of a pre-existing fault. So that's the main point. You can map before, and it is different from rank 2, which are random, which occur in places where you have no data to predict the occurrence of a distributed rupture before the event.
Okay, I was wondering how is it different than rank 3, which is triggered?
Rank 3 is on a fault very, okay, this is a matter also of distance. For example, rank 3 is a reactivation of a fault that can produce a principal fault also from itself. You know, you can have a very far fault that can produce a principal rupture, but that can also be reactivated as distributed due to a very far principal fault on a different main fault. So this is, yeah, distance is also matters in this case.
Okay.
Great. Thank you, Paolo. Thank you,
Paolo.
Lisa. Thank you, Fia. Appreciate that. And also, I think Alex put the link to their publication also. Great.
Great, yeah. All right, I think we're nearing the end here, so we might be done for questions, but please reach out, of course, if you have more questions, or come back on Wednesday, which is a good segue into just the last thing I want to say every time. What's this, the sharing? I'm trying to share the agenda here. Share the agenda. There we go. Perhaps the agenda is showing. Yeah, good. So let's please, I hope you're able to join us again on Wednesday at same time, same place, at 10 a.m. We will have some lightning talks in the first half of Wednesday, and then we will talk in more detail about the new fault displacement models that we mentioned earlier today. So please come back on Wednesday, and I will start. And then maybe I will mention that on day 3, we will compare the results of the new fault displacement models, talk a little bit about the available code, and then Dr. Thompson kindly has pulled together a suite of example applications to help us understand how to handle these metrics and definitions and whatnot. And with that, maybe we'll turn it back over to Dr. Berzonia.
Thank you, everyone. Appreciate that. So we'll come back on Wednesday. You're going to receive a PDF of the slides and also the link of the recording. So if you want to review, and then if you want to contact us with more comments and questions, perfect. And it will, all the questions and comments are welcome. Thank you again, and we'll see you on.
May I make a special request?
Absolutely.
The slides were wonderful today, but so many of them had so much information. And while the speaker was talking, it was very difficult to see which part of the slide he or she is referring to. So please, could you use the mouse or something so that we can follow you? It was really difficult, especially some of the slides had so much information, it was almost impossible to follow. And I really would like to get, this is a fascinating workshop.
Very good comment, as always.
I want to get the most out of it.
Absolutely, and it's a great comment, and we'll follow that on Wednesday and Friday. As always, Professor Idris, thank you very much. Thank you, everyone. Appreciate that. Wednesday, 10 o'clock, 10 a.m. Pacific time, and we will continue. Thank you. Thank you. Thank you.
Thank you.